Yeah, good morning and welcome to the seminar. I would like to present today one of my new working papers, and this paper is entitled Option-Implied Volatility-Managed Asset Pricing Risk Factor and Resurrection of the Value Factor. So, what is it all about? So there is some recent literature in the top finance journals that investigate the effects of volatility timing. For instance, early papers from Fleming, Kirby, and Osti, JF and JFE paper, they studied the effects of volatility timing on different asset classes. And in their paper, they studied stocks, bonds, and gold. In the 2016 JFE paper, Daniel and Moskowitz, they studied the effects of volatility timing, the momentum strategy, using conditional volatility models, such as gauge type models, and then one step ahead forecasts. And what they argue that using this volatility timing almost eliminates the momentum crash risk. In a paper that is related to Daniel and Moskowitz study, Borossi and Santa Clara, the 2015 JFE paper, they studied the effects, they studied also the effects of volatility timing the momentum strategy, but they used a 6 months time window of realized volatility for estimating the scaling factor. And they find the same thing like the paper from Daniel and Moskowitz, that in employing this volatility timing strategy decreases this momentum crash risk. In a more recent paper, the 2017 JF paper from Moreira and Moore, they propose volatility-managed risk factors, incorporating using the most recent realized variance of the most of month t minus 1 for compounding their scaling factor. So they use the realized variance using a shorter time window, but also in Santa Clara use the realized volatility and a longer time window. And the difference between Moreira and Moore's paper and Borossi and Santa Clara, or Daniel and Moskowitz, is that they investigated and French 6 risk factors, and in addition to that, the return on investment or the return on assets strategy and the carry risk strategy from the currency market. So in total they have 9 different portfolio strategies where they estimate these or where they investigate this volatility managing strategy. But how does it actually work out? So if we have a strategy or if we have a portfolio, let's say portfolio RI, portfolio I at time t. That's this can be anything. It can be the size factor, it can be the value factor, market portfolio, whatever. Yeah? So we have to multiply it with something, and in the denominator we have a constant. This is just the scaling factor here, and this is referred to in the paper from Borossi and Santa Clara as target level of volatility. So when they set it to, they say, okay, in our paper it's like 60% per annum. Yeah? So, but it doesn't matter, because whatever scaling factor you choose, if you estimate error on the Sharpe ratio, it doesn't matter. So in the denominator, we have the expectation of something of, let's call it Wt, given time t minus 1. So you have the expectation of either the volatility or the variance, depending on what you want to use for your scaling. And that's then, in essence, the R sigma of portfolio I at time t. Yeah? So that's the scaling factor. This guy here. That's time variance, obviously. Yeah? It's denoted as, let's say, St. Yeah? If you would plot it over time, or St, the scaling factor, then you would get something like this. Moves up and down, depending on the volatility or the past volatility or past variance. So in the middle we have like 1. If the scale factor is 1, the risk managed counterpart is equal with the standard strategy. Whenever it is larger than 1, we leverage our position in this area here. It's larger than 1. So here we would buy, let's say, we would leverage it times 2. So we would invest twice. So we would go to the bank, get credit, and invest twice in this 200% in this strategy. Whenever it is below 1, And this area, we will deleverage our position hold in that portfolio. This is 0.7, we invest 0.7 into, let's say, size anomaly, and 0.3 we put on the bank account. So now, the difference between all of these papers here is simply the way how they calculate this guy here. So this WT. Because it can be, in the paper from Vaasa and Santa Clara, they use the six months realized volatility, so it can be the realized volatility. They use the most recent month's realized variance, so it can be the realized variance of our portfolio RIT. Yeah. The other papers use some gauge type estimated 1 month ahead forecast of portfolio RIT. So there are many different candidates, obviously, that have been discussed. But that's basically the idea. So the commonality, what all of these papers have in common, because this is what we're interested in. We are interested in commonalities in science, right? What do they have in common? So all of these papers report that using this volatility timing, whatever strategy you choose, expands the mean variance frontier. So for each given level of risk, we get a higher return. So what about the idea? So Vaasa and Santa Clara, in the 2015 paper, they argue that in unreported results, we find that forecasting the risk of momentum with the realized variance of the market in the previous 6 months produces a very similar result. So there are alternative methods to manage the risk of momentum and exploit its predictability. In table 7 of the paper from Marua and Moore, what they do here is they use this they estimate the realized volatility of these 9 time series here, and then they take the first principal component of these, which is in essence basically the force that drives the volatilities of these 9 factors in the same direction. And then they basically use the first principal component of this 9 time series of realized variances here in the denominator of this formula. And then they estimate it again. They compound the alpha, which is the part, they regress the risk management strategy on the standard counterpart, and the part that is unexplained, including a constant term in the regression equation, and the part that is unexplained, that the constant term is the alpha. This is what they report here in this table, the annualized alpha. For instance, for the market factor, once you employ this volatility timing strategy, you get an alpha of 4.22%. And what they report here in parentheses, which is unusual for the Journal of Finance, because they usually report these statistics, right? But here they report standard deviation, so you have to divide the point estimate by the standard deviation. If you do this, you will recognize for the market factor, for the value factor, and for the momentum factor, if you just restrict our attention to the found French 6 risk factors, right? So you will see that the t-statistics are larger than 2 for these 3 candidates, implying that this strategy works out even if you use the first principal components of these 9 realized volatility series. So there's obviously one common factor that drives all of these volatilities in the same direction. And obviously it even works out if you just use the market. So in the 2017 paper, Morella and Moore, they argue that using an equal weighted average of realized volatilities, or even just the realized volatility of the market factor of the market return, produces similar results. So they say actually the same as in the paper from Vaasa and Santa Clara. So why would it be like that? So here you see basically the realized volatilities of these risk factors here, the market factor, value factor, size, momentum, profitability, investment, and the carry factor. Yeah? What you see is obviously they move in the same direction over time. So they have some common component. And this is what principal component analysis is about. So they basically use this, they expected the common component of this volatility series for estimating this denominator here. Yeah. This is basically the idea of table 7 in the paper from Morel and Moore. But now, knowing about this, what's the problem with all these approaches? Who's our option expert here?
Sparse information.
Exactly. Exactly. Actually, I wanted to ask Sami this question, but since he is not here, Jan is a good alternative. Yeah, exactly. So, in an early paper, Christensen and Prapala, this is a JFE paper of 98, so it's a very early paper, they argue that path volatility has no incremental explanatory power over implied volatility once path volatility is controlled. What does it mean? Well, if you regress option-implied volatility and lag path volatility on realized volatility at time t, the lag regressors of path volatility have no explanatory power in the equation. So it's option-implied volatility that actually is the best predictor for realized volatility. Using estimated historical variance as a variance forecast is statistically not appropriate as it does not incorporate market participators' expectations very late. And from a practical point of view, realized variance or volatility estimates might not easily available to the naive investor. You can maybe ask your neighbor if we ever which kind of realized volatility estimate he or she might use. It's obviously not so easy available to the naive investor because what is it actually? Moreover, there are various methodologies available for compounding realized volatilities. And there's a literature review from McElia and Medeiros in the econometric reviews that discuss all of these different estimates. So how does this study contribute? Well, this paper reinvestigates the effects of volatility-managing risk factors by using the VIX, as the VIX reflects the market's best assessment of the expected volatility of the underlying stock index, according to Whale. Specifically, this paper investigates two different strategies, using either the high VIX or the low VIX of the previous months before asset allocation. And this approach enables us also to explore the difference between pessimistic and optimistic investors, right? Because an optimistic investor will use the low VIX estimate. Yeah? He will underestimate, systematically underestimate the volatility. And the pessimistic investor, an anxious investor, will overestimate the volatility. Yeah? They will use the high VIX. So, and unlike Morel and Moore, what is also different in my paper, that the option-implied factor models, they are compared with the traditional counterparts using Farmer and French new econometric method. Yeah? Because actual estimates of the in-sample Sharpe ratio are outwards biased because they maximize in-part on sampling error, as noted in the JFE paper of Farmer and French. So what I do is a simulation study based on past bootstrapping. But we'll come back to that soon. Moreover, this study satisfies the requirements of a scientific replication in line with Habermas, because it first uses a sample period that is different from Rosso and Santa Clara and all the other papers, because data for the VIX is simply not available ex ante 1990. And second, it uses a similar but not identical model, because I use the expected volatility, the VIX, instead of past realized volatility. According to Hu, Xu, and Zhang, they note in their 2018 RS paper that it is critical to evaluate the reliability of published results against similar but not identical specifications in finance. Because as finance as science is mostly observational in nature. So what they authors are doing, and actually I highlighted this paper also in the trial lecture, so they investigate 452 different asset pricing anomalies, and they figure out that 65% failed the replication. Using a higher threshold accounting for a t-statistic of 2.78, like if you account for multiple testing, then even more, like 80% fail the replication. So that's why it is important to reinvestigate if results are really robust. Obviously, markets are much more efficient than you might think. What's the model setup? Well, the general framing is the same, of course, as in all the other papers. So for the motivation for the strategy comes from the portfolio problem, simply of a mean variance investor who is deciding how much to invest in a risky asset. For data I use monthly data. I download the monthly data for the market return, size factor, value factor, probability factor, investment factor, and the momentum factor from the Spanish website. Data for the VIX is retrieved from here. Sample period, because of the data availability of the VIX, starts in January 1990 until July 2009. And the model setup is very similar to what I have already elaborated here on the whiteboard, right? Just here what can you see in the denominator, obviously. I have now the expected volatility, and I use the VIX. And it can be either, I have two different strategies. I take the lowest VIX and the highest VIX. One strategy is systematically overestimating the volatility in the next months, and the other one is systematically underestimating the volatility of the next months. So we have an optimistic and a pessimistic investor here. The results. So this is an excerpt from figure 4 in Vaasa and Santa Clara. Here the upper figure, and their sample ends in 2010, in December 2010, and I cut off here the beginning of the time window, so that you can see the overlap here, between what they report and from my estimates. What you see here is that doesn't matter if you use VIX or if you use the 6 months time window. If you use, of course, the 6 months time window, the time series is obviously much smoother. But you see, we have a similar stochastic movement going on here. So in the early 90s, when volatility is low, the scaling factor suggests to invest to leverage our position. This guy is larger than 1. So this is what you see here for both. If you use high or low VIX. So the stochastic movement is the same. We have a spike here in the early 90s, and the same is for the strategy employed in Vaasa and Santa Clara. So both strategies suggest to leverage the position hold or kept in this portfolio. So and the second, also here in the early 2000s, when volatility is high, the dot-com bubble bursted. It started in the US, and the whole world came into the recession. Obviously, volatility was high, and our strategy suggests to deleverage the position kept in our risky assets. So we have the low, the scaling factor is low, and it's the same here for the strategy employing the VIX. And you see here also, I basically highlighted the areas where the NBER reported recession dates. So whenever there's a recession going on, our strategy suggests to deleverage the position hold in the risky asset.
Sorry, may I ask?
No.
Okay,
Yes, of course.
afterwards.
Shoot.
I was just thinking, so the scaling factor is the same for all factors.
And this is just momentum.
But for you?
Here? Exactly.
Yeah.
Exactly. Because why do I do that?
Principal components.
Exactly. Because these papers here, they note that basically these papers actually note you get similar results if you use just the market factors volatility or variance instead of using the factor-specific variance. And why is that? Well, because there's high level of core movement in the realized volatilities.
Just as a further idea, I would say, there could be something that the certain factors go very differently with volatility. Sometimes momentum goes crazy when volatility spikes, sometimes carry or sometimes others. So there are some spikes also over there that certain factors respond differently to increases in volatility in markets.
Yeah, of course, you get, of course, slightly different results.
Just as a
Yeah.
idea for further consideration
Sure.
at least.
So next, I report in this table the summary statistics. Here in the first, I focus on the time and French, 6 risk factors here. So in the first row, you see the standard risk factors. In the second row, I report the results for volatility managing using the high VIX. And in the third row, I report the payoffs of the volatility managed factor portfolios using low VIX. And in the last row, I report the factor spread between low minus high VIX. Once again, low VIX means optimistic investor, underestimating the volatility in the next period, and high VIX is a pessimistic investor. So it's like low minus high is the same like optimistic and pessimist. So what you see is here, if you consider just the market factor here, so the payoff, if you employ the high VIX for compounding the scaling factor here, the payoff is lower than the standard strategy, but the t-statistic is higher. If you are an optimistic investor who use low VIX here, the payoff is higher, and also the t-statistic is higher than the standard part. If we take the return difference between the optimistic and the pessimistic strategy, it's positive, it's 21 basis points per month, with the t-statistic of 2.87. So the difference in payoffs is significant on any level. For the size factor, you see there is, first of all, it's obviously, it doesn't generate any payoffs, not even for the standard strategy, and volatility managing doesn't make it better either. Similar for the value factor. And now you might wonder, okay, why is the paper entitled Resurrection of the Value Factor? We will come back to that soon. For the profitability factor, we see similar evidence. The payoffs are 35 basis points per month. If you use the standard farm and French strategy, using operational profitability, and if we use high VIX, so a pessimistic investor, it generates lower basis points. It drops from 35 to 25 basis points, but the t-statistic increases. If we are using low VIX, the t-statistic or the payoff is almost the same as if we would the standard strategy, but the t-statistic is again higher. And similar evidence we see here for momentum. So there is evidence for that we have different effects using high or low VIX. And for the market factor, the profitability factor, and the momentum factor, the return difference between low VIX and high VIX is significant on 1% level. Next, I report the maximum squared Sharpe ratios. So I use these risk factors here and estimate, okay, what's the maximum squared Sharpe ratio of the frontier portfolio? I have the actual values here, and then you see SS means full sample, IS means in sample, OS means out of sample. So what does that mean? Maybe I can take back this here. We have discussed that. So the actual estimates are straightforward, right? So that's obviously no deal. So we employ this portfolio maximization problem, and then you get the estimate. So using the standard Hamilton French risk factors, the maximum squared Sharpe ratio of the efficient frontier portfolio is 0.1452. Employing either high VIX or low VIX for risk managing all these risk factors here, it results in higher maximum squared Sharpe ratios. But the difference between high VIX and low VIX is not much. It's very, very similar. So based upon that, we cannot make any inference. So Farmer and French, they report now the results for 100,000 replications. Yeah? They call it full sample estimation. So they want to see, okay, these estimates here can be sample specific. So they simulate artificial samples of risk factors. So what they do is, let's say, that's our data matrix. We have 6 risk factors, and this 10 doesn't make it. We take this one. So we have 6 risk factors, and we have here the time dimension. Yeah, T is 1, T is 2, until capital T. And in my case, I have 354 observations. So what I do is, okay, I randomly draw one row vector of this data matrix, put it here, put the row vector of risk factors back, and do the same again. Yeah? I do it 300, it's random drawing with replacement. So I do this 354 times, get a new data matrix, and then I do the same 100,000 times. So I construct 100,000 new data matrices of risk factors using this simple fast bootstrapping. It's fast bootstrapping because it takes the whole row vector here. And then I compound the average maximum squared Sharpe ratio over the 100,000 simulated samples. And what you see is we get slightly larger numbers here, but still the maximum squared Sharpe ratio using high and low VIX for risk managing the risk factors here generate higher maximum squared Sharpe ratios than using the standard risk factors. So the problem is, if we use full sample estimation, as reported in Farmer and French, that there's a bias going on. So it's upwards biased. So what the authors of Farmer and French then suggest is, okay, we do an in-sample and out-of-sample simulation. And I did the same thing. So how does this work? Well, we have now 2 different data matrices. So we have here the actual data, and we simulate, we draw randomly one of these rows. Let's say, okay, in the first iteration we get this one here, so we put it here, we put it here, it's our first element obviously, in our data matrix, in our new data matrix. And the second element, the row that follows here, the row afterwards, we put it here in the out-of-sample matrix. That's our out-of-sample matrix. And then we do it again. In the next iteration, we might get this guy here, this row. We put it here. This will be our second row in the in-sample data matrix. And the row that follows here, we put it here. It's the second element in our out-of-sample matrix. Then we estimate the maximum squared Sharpe ratio. We get the weights using the in-sample data matrix. We keep the weights constant and run it for the out-of-sample matrix. And that's what we get here. These estimates are unbiased. And what we see is, using this approach in Farmer and French, that the difference is now larger. The difference between our risk-managed strategies and the actual strategy here using the standard factors, the difference in maximum squared Sharpe ratios is even higher. So next, we are wondering, okay, are the values for the maximum squared Sharpe ratio statistically distinguishable? Because now we still have different point estimates. So what we do now is, using the same strategy, so the same methodology, I report in this table here how often in how many runs is the row model performing higher or getting higher maximum squared Sharpe ratios than the column model. So here the first one here, the column model is the standard Kalman French 6-factor model, and here, for instance, the second row is the using the high fix for our scaling the risk factors. So in here the point or the estimate of 96.9 means in 96.9 of 100,000 simulations, this model here generates a higher maximum squared Sharpe ratio than the standard model. So overall, these results here on the right hand side suggest that both models, and it doesn't matter if we use out of sample, in sample, or full sample simulations, in at least 87.19% of the runs, one of these volatility managed risk factor models performs better than the standard 6-factor model. What we do here is I compare now the volatility managed risk factor models with each other. And what we see here is, for instance, let's consider the last row here. So in at least 85.57% of this 100,000 simulations, out of sample, using the high VIX for the scaling factor, that generates higher payoffs or higher maximum squared Sharpe ratios than using low VIX for the scaling factor. This tells us that employing volatility managed risk factors using the high VIX estimates, it generates better payoffs than the volatility managed strategy using low VIX estimates. So in the factor model, it's obviously better to be more pessimistic. Now we want to know, okay, what is the driver of this result? Yeah? Why is it like that? Why do we get these results? So which risk factors, which volatility managed risk factors are actually the cause for this effect? So what I report here is using, in this table here, I use low VIX volatility managed portfolios. And I regress the volatility managed portfolios in panel B on the Kalman French 6-factor model. So the intercept, and I report the intercept of this regression equation. So the intercept tells us the part of the return on this portfolio that is unexplained by exposures against the 6-factor model. And what you see is that only the value factor and the volatility managed momentum factor, they generate alpha. So they have T statistics of 2.65 or 4.23. And these are the monthly alphas, okay? I report here the monthly alphas. So you have to multiply this by 10, by 12, that you would get the annualized estimates. And we get the similar result if we use the high VIX volatility managed portfolios. It's the value factor and the momentum factor that are driving the results. So these are actually these two risk factors that actually generate excess payoffs after controlling for the standard Kalman French risk factors. They drive the result. Similar, Kalman French found in the recent 2018 JV paper that the size factor generates alpha once it is controlled for the 6-factor model. Summary of the results. So, as argued at Kalman French 2018, whose findings indicated that the size factor generates alpha in spanning regressions. The results show that average returns can be misleading for judging the importance of factors in multi-factor models. So we should control for the other factors. And what we have seen is value factor and momentum factor both generate alpha. So the reason for why option-implied volatility-managed risk factor models outperform is that the option-implied market volatility captures obviously information about future payoffs. For some, but not for all risk factors. Brief discussion. Now we come back to the to table 7 from our and Nuno's paper. So once again, they use the first principle component of this 9 realized volatility series for scaling the factor payoff. And in their analysis, it's also the value factor and the momentum factor that generate alpha. Here they report the underlying numbers, by the way, but also the market factor. Surprisingly, I do not find any evidence for the market factor that the market factor would generate alpha. If we go back to the tables here, the T statistic is 0.64, respectively minus 0.13. Some concluding remarks here. Well, this study investigates the effects of option-implied volatility timing on risk factors to form a French 6-factor model. Supporting earlier literature, I find that volatility managing using VIX expands the mean variance frontier. If we take the overall view, investors running an optimistic timing strategy for the market factor, profitability factor, and momentum factor are compensated by higher returns than pessimistic investors. This is where the results from the univariate table, the first table I reported. But using the factor models, the whole set of factor models, we find that the pessimistic market timing strategy outperforms in terms of maximum squared Sharpe ratios in both full sample, in sample, and out of sample simulations. The reason for why option-implied strategies generate higher maximum squared Sharpe ratios is that both the momentum factor and the resurrected value factor generate alpha. Thank you. That was my presentation. Now I'm welcoming